So, where are we? We have been talking about local search, and in the context of local search, first we talked about how to define the state space, and then we have been talking about various algorithms. And the first algorithm we talked about was greedy local search or hill climbing, and we realized that actually it gets stuck in local optima. And a natural way to look at how to improve this was by using stochastic variations, in particular merging either random walks or random restarts with hill climbing. And in the context of random walk, we can say that with some probability take a random action, with another probability take the greedy action. In the context of random restarts, we can say go greedy for a long time. If you are stuck or if you are sort of done for whatever reason, you restart from a random point. So, jump to a completely different part of the state space and start going up again. And then I also went as far as saying that if there is one algorithm you need to take back, this should be it, because this is my favorite algorithm. Whenever I have a problem which I like to model as local search, which are often many problems, the algorithm that I implement the first is hill climbing with random restarts. And there is a question on that. Yes?
So, when we are stuck at a minima,
yeah.
then we restart, but what if that minima was the global minima?
Then we keep restarting, at some point we are done, our time is up, and that minima remains the best. So, we always, so the question here is that what do I do if that minima was actually the global minima? That is great. You have found it, you will keep searching, you will never know that it was the global maxima or global minima. You will keep searching, and at some point you will say, oh, I am done searching, I am tired of searching because my time is up. So, now what do? Well, I return the best solution found so far. So, local search has this property that if you give it 5 minutes, it will give you an answer in 5 minutes. If you give it 1 minute, it will give you an answer in 1 minute. If you give it 1 hour, it will give you an answer in 1 hour. And hopefully, the answer that it will get in 5 minutes will be better than the answer that it gets in 1 minute, and 1 hour will be better than 5 minutes, because it will keep searching and hopefully it will get to a better optima, right. And then you can also do hill climbing with both. You can do, with small probability take a random action, with small probability take a random restart, and otherwise keep doing greedy. Okay. So, this is the general principle here, that we have to somehow incorporate these random actions in the context of greedy actions. And one of the more famous algorithms which achieves this is called the simulated annealing algorithm. Okay. And the idea of simulated annealing is that it is nothing more than a random walk with greedy hill climbing, but the random walk happens in a specific fashion, and that specific fashion allows you to say interesting properties about this algorithm. And so, what are the basic ideas? It is like hill climbing, except instead of going through all the neighbors, you pick one randomly. So, I think that was a suggestion made by somebody in the class long time back, that if I find the first better move, should I just jump there? It is actually even more interesting than that. So, it says pick one random move, okay, of my neighbors. Do not even go over all the neighbors, just pick a random move from my neighbors, and then think about whether you should take this move or not take this move. So, if it improves the objective function, take this move. So, okay. So, look at all the neighbors, no. Take all the neighbors, find a random neighbor, only look at this random neighbor, first step. After you look at this random neighbor, figure out whether its objective function is better than my objective function. If it is better, go there and repeat. If it is not better, that means it is a worse neighbor. What should you do? Do not stop and do not think you are at a local optimum. No, with some probability you may still take this bad move. It is a bad move, but with some probability you will take it, and the probability will be determined based on how different the objective functions are, how bad it is, and whether you are in the initial part of the search or later part of the search. Okay, those are the two properties. So, what it says, so say that we are in the maximization world. So, let us say the change in objective function is delta. So, if delta is positive, If delta is positive, move to that state. So, if it is a good state, go there. Otherwise, move to the state with probability proportional to delta. In other words, the delta is now negative, but less negative means higher probability of going there. And of course, when we say proportional to delta, it is not directly proportional, it is not linearly determined, because why? Delta can be negative, in fact delta is negative in this case, and probability is always positive. So, we need to figure out, and delta can be between 0 to minus infinity, probability is always going to be between 0 and 1. So, we have to somehow convert this delta into a positive number and a probability. Okay? So, what is one function that takes any number positive, negative and converts it into a positive number? Sigmoid. You guys have been reading a lot of deep learning, sounds like. Who taught you sigmoid? No, that is not incorrect, it is correct, but I was expecting something simpler. The exponential function, right? E to the power, that is sigmoid. Sigmoid also has exponential function inside it, go check it out. So, sigmoid function absolutely, but the general principle there is the exponential function. So, you will take the exponential function and apply it over delta, right. So, now what is happening is you are moving to the state with probability proportional to delta. So, worse moves, very large negative delta will probably not be executed very often, right. If this state looks so bad than me, then I will be rather dumb going there, but with a very small probability I will go there, with a very high probability I will not go there. If the state is sort of less than me, but not too much, then I will probably go there with a high probability, right. So, this is sort of the idea of simulated annealing. However, these bad moves over time should increase or reduce? Reduce. See, initially I do not know anything, I can move any which way, but later as I feel I am in the right neighborhood, I should not be making these bad jumps, I should be trying to go up and get to the peak, right. So, that is sort of the idea. Over time, make it less likely to accept locally bad moves. Okay. So, this is the algorithm. You are at a current state from t equal to 1 to infinity 2, capital T is the schedule. Okay. So, now this capital T is something very interesting. This is called the temperature parameter. Now, why is it called the temperature parameter? We will talk about it, but for now let us say it is a temperature parameter which says that if it is too hot, your brain is fried, so you can make a lot of bad moves, but if it is too cold, you are very calm, and if you are very calm, you will be making the right decisions and you will not be jumping towards a bad move. So, that is the idea of temperature. Temperature too high, it is okay to take a bad move, temperature too low, it is less okay to take a bad move. Okay. And so, how do we operationalize this? If we set t equal to 0, that means I have become so cold that I have frozen. If I have frozen, then I can't move anymore. If I can't move anymore, return the answer, right. Otherwise, my next state is a randomly selected successor of current. Notice that it is a random selection. I am not optimizing, I am not going over all neighbors and doing anything greedy. Now, delta E is the value of next minus value of current. If delta E is positive, life is good, the current is better than next, I jump. So, current is equal to next. Sorry, next is better than current, I jump, current is equal to next. On the other hand, if delta E is negative, that means next is worse than current, but then how much? Why delta E? So, I will take that move with probability e to the power delta E by T, capital T the temperature. So, notice that if delta E was very bad, like minus infinity, this probability would be 0. If capital T was 0, this probability would be capital T is 0 and delta E is always negative. So, this is negative divided by 0, which is e to the power minus infinity is 0. So, if my temperature is too cold, then I don't ever make a bad move, and if my delta E is too bad, I don't ever make a bad move. But if delta E is slightly bad, I make a bad move, and if the temperature is high, then I can make a bad move with higher probability, right. So, temperature parameter says high temperature probability of locally bad move is higher, low temperature probability of locally bad move is lower. Typically, notice that I said capital T is a schedule. Where is this schedule coming from? Well, somebody provides it, and this schedule should say that as small t increases, capital T should decrease. Exactly. So, this is called the temperature schedule in simulated annealing, and as t is decreased, the algorithm runs longer. Yeah, as the algorithm runs longer, capital T, the temperature is decreased. Temperature is decreased really slowly in practice. Yes. Is it more likely to be stuck in local maxima or less likely to be stuck in local maxima? What is your hunch? Well, yes. Why do we only want the schedule to be dependent on time? Why do we also not consider the difference in the objective functions between current and next? I guess that the difference in the objective functions between current and next does not give you that much information because it is a random neighbor. So, average of last current and maybe, I do not know. I mean, I have not understood the full theory of simulated annealing to figure out what are the various bells and whistles. But to the best of my knowledge, you use this temperature parameter to prove properties of the algorithm, and the theorems say that if a temperature decreases in a certain fashion, then certain properties hold. Okay, so, you do not need it to be dependent on delta E for the properties. Now, that said, it is possible that if you somehow make that tweak, simulated annealing in practice runs much better, and that part I need to check. I am not entirely sure about. So, your hunch is sort of wrong. I understand where your hunch is coming from. I mean, I do not disagree with you. We are taking so many bad moves all the time, you feel. So, therefore, it should be worse. But actually, a lot of it depends on the temperature parameter. So, let us think about what is going on. So, suppose I have a ball that I drop at the top of the peak, and my goal is to have it go to the very bottom, like reach the river, right. So, imagine letting a ball roll downhill on a function surface, right, and so it starts going down and it gets stuck in a local minima. Now, imagine that you are shaking the surface. So, earthquakes are happening and God is playing simulated annealing with you on the mountains. So, initially you shake a lot. So, if you shake a lot, what is going to happen? Any kind of a small local optima, any local optima, because the shaking is too much, it will be able to jump off it. And once it jumps off it, it starts going down further, and there is shaking going on, so it starts going down further. Slowly, the shaking reduces, and eventually earth gets formed. So, the question you have to ask is, where is the ball? Is it still stuck in somewhere in the local maxima, or has it reached the river? And the theorems say that the probability that you would have found the global optimum is very high, gets towards 1 if the temperature, if the shaking is reduced slowly. So, you start with a lot of shaking, but then slowly, very slowly you reduce the shaking, till infinite time you are guaranteed that you will reach the local optimum or global optimum with probability tending to 1. So, this is the physics analogy of what is going on. And another analogy, physics analogy, comes from the field of statistical physics, where they look at how these materials crystallize slowly. So, this is called annealing. In fact, that is where the name of the algorithm comes from. Annealing is the physical process of cooling a liquid or a metal such that particles achieve a low energy state. and then the particles have spins, and if they are in the opposite directions, then they have a certain behavior. If they are in the same direction, then they have a certain behavior, and you are trying to look for the lowest energy configuration. And so what you do, you start with a very high temperature and you slowly reduce the temperature. As you keep reducing extremely slowly, the metal or the liquid crystallizes and becomes a very strong solid, and that is called the process of annealing, right. So, each particle is like a free variable, they are trying to seek a low energy configuration, which is our objective function, and slowly reducing the temperature leads you to an energy state which is highly crystallized, highly strong in its form, and that is sort of the intuition that we are trying to model in this algorithm. In fact, you can think about simulated annealing as if it is your life, as always. What is this temperature parameter saying? Temperature parameter initially is saying is, oh, you can go there, or you can go there, or you can go there, it is okay. You can go anywhere you want. And as temperature reduces, you are saying, no, no, that move is bad, don't go there. No, no, that move is bad, don't go there. Go to this move because it is better move. So, think of a child. The child has very little definition of the objective function. It is not trying to optimize it. The child is always trying to sort of explore and try things out and putting everything in the mouth and doing everything. Of course, there are better analogies for why the child is doing it, which we will learn towards the later part of the class, which is reinforcement learning. But at least in this limited context, the child's behavior can be seen as the behavior of simulated annealing, because initially the temperature is too high, the child is sort of taking any move whatsoever for whatever reason, we do not know. But as they become older and more older, like me or my parents' age, they have their ways of doing things, they know exactly how to climb the hill. You can't make them budge, right. So, this particular intuition we will come back to in reinforcement learning, where we will discuss exploration exploitation trade off. But one way of thinking about the fact that you can do more exploration or more exploitation is in this context of simulated annealing and temperature parameter, where initially, because you can take a lot of random moves, a lot of bad moves, you might be saying that, oh, even though this move looks bad, let me go there, because it is possible that I will reach a hill through this process, which would lead me to the optimal solution. So, that is sort of like exploration. Whereas later, when your temperature parameter is reduced, you are not taking bad moves, you are only taking the greedy moves. You are saying that, look, I am now interested in maximizing the objective function, I do not really care for many other exploratory moves. So, in practice, simulated annealing was a very successful algorithm. It was a method proposed in 80s by IBM researchers for solving VLSI layout problems, believe it or not. So, you have a large you have a lot of these transistors and wires and so on and so forth, like a very large scale hardware, a chip that you want to create in a very small space, and so you need to optimally place them, or place them as well as possible, so that the wires are far from each other, so that there are no errors and functionality and so on, but you are using the given area effectively. And so, they were able to prove that theoretically it will always find the global optimum. Of course, that was never achieved in practice, because for theoretical properties the temperature has to be decreased so slowly that it becomes a useless algorithm, right, very gradually. So, in practice people would reduce the temperature relatively quickly, so that they do not necessarily reach global optimum, but they still used to reach a very high quality local optimum, right. And you can always do the trick of best algorithm found so far, best solution found so far, you will maintain some. So, it had a lot of applications at the time: traveling salesman, graph partitioning, graph coloring, scheduling, facility layout, image processing, and so on and so forth. So, it was a famous algorithm. There was a question. If we know the time beforehand, we have to learn the algorithm for a certain amount of time, yes. So, then you will have to decrease the temperature quickly, exactly. You cannot decrease it extremely slowly, which is what these guys would also have been doing, because in the 80s your computers are not as powerful as you want, as you have today, and if they have real interesting problems, then they do not have the luxury of reducing the temperature very slowly. So, they would reduce it somewhat reasonably. That makes sense in the context of your given time, exactly. Okay. So, this completes the subsection of local search with stochastic algorithms. No, that does not complete that subsection, but we have now been able to achieve some kind of global optimality. That is the point I was trying to make. By doing hill climbing with random restarts, by doing hill climbing with random walk, by doing simulated annealing, all of these are asymptotically optimal. In the limit of infinite time, you will get to the global optimum for whatever reason, different reasons, right.